Alright, so now we are switching to English. Well, this tutorial will be about orthogonal bases, matrices, and a little bit about how this relates with linear systems. And first of all, let's start with what is a basis. A basis is defined by two properties. Do you know the properties?
So first, the vector has to be linearly independent.
Yes, the first one is linear independence. And the second one?
It has to be a subspace of the same space.
Yeah, the second one is that the linear combination of those vectors generate the space. So, for example, in this image, I show these purple vectors and these red vectors, and as you can see, they both generate the same vector. So there's multiple ways to write a vector with different bases. So a basis basically is a set of these vectors that can generate any vector in this space. In this case, I'm showing R3, well, the 3D space. And just a reminder, the properties that these vectors v1 until vn needs to satisfy to be a basis for the vectorial space V is that the linear combination between them, the span is the collection of all the possible linear combinations of the vectors. Okay? And those linear combinations needs to generate the vector space V. And also that the linear combination needs to be linearly independent. That this is the most obvious one. Jorge, yes, I'm recording. Okay, so what's the big fuss about orthogonal bases then? We have regular basis vectors. Why do we need an orthogonal basis? Some of you have an intuition why this is the case? Why an orthogonal basis could be better than a regular basis?
To define better the coordinates.
What do you mean with that? Can you explain a little bit more?
I mean just that the weight of each, when the coordinates represent the weight of each contribution of the vector to the vector, and so in an orthogonal base, as they are all perpendicular, so you have all the contributions that are unique for this vector.
Yes, you have the right idea. It has something to do with the coefficients that go along with the vectors. So, to see why that's the case, I'll use an example. My example is, let me show it again. Let's say we have a vector x that belongs to this vector space V that is defined as the collection of all the linear combinations between the vectors v1 and v2. Obviously, here I am assuming that this v1 and this v2 vectors are linearly independent. Okay, such as x equals to alpha times v1 plus beta times v2. What are the coefficients alpha and beta? That's the question. So we had x, that's a little weird color, x equals alpha times v1 plus beta times v2. How can we obtain this coefficient? For example, the alpha coefficient. What operations we need to do to this to get only the alpha? Have you seen this example in class or something similar? First, let's assume that...
Vector product.
Sorry, what? It was a little bit... the audio was not clear.
Yeah, sorry. With a vector product. So if they are orthogonal, they will make null the contribution of the vector.
Yes.
The orthogonal vector.
So if v1 and v2 are orthogonal, that's denoted by this perp symbol, that's the same as saying that the inner product between v1 and v2 is equal to 0. That means that, for example, if I want to get this v1 coefficient, I need to do the inner product of this expression, whole expression, with v1. Let me delete this arrow. After doing this, delete the left hand side, v1 x. Here you have v1 plus beta times v1 v2. By definition, this is equal to 0, right? So automatically we arrived as, I'll go one step further and say that alpha equals to the inner product between b1 and x and b1. The good thing about this is that, one, we can easily get the coefficients that go along with the basis vectors. But another thing is that the coefficient does not depend on the other vectors on the basis, just this first one. For beta, you have the same, but instead of v1, we would need to do the inner product between the expression and v2. So we arrive at this. And this denominator here, it's also equivalent to what it's called the norm of the vector, but squared. This is also the norm of the vector v2 squared, right? So this is the great deal with orthogonal vectors. We can have the coefficients very easily. And there's another brother to the orthogonal basis, that is the orthonormal basis. And the good thing about the orthonormal basis, this is for orthogonal basis. And if I have orthonormal bases, normal, that means that each of the vectors in the basis have a norm that is equal to 1. And that one is a little bit ugly. Yeah. And you can see now that the expression to arrive to the coefficients is even easier when the basis is an orthonormal basis, because the denominator disappears, right? Everything clear until here? Clear? Okay. So we arrived that the orthogonal bases are great because we can write the coefficients that go along with the vectors using this inner product that is defined as this summation. Okay. In class, you saw this expression without this asterisk. This means the complex conjugate, because these vectors can be complex, but if the vectors are real, or another, yes, if the vectors are real, you don't need to consider the complex conjugate. Okay, so how can we generate an orthogonal basis from a regular basis? This is where the Gram-Schmidt process it's relevant. If you have a collection of just vectors, you can create an orthogonal basis by using this Gram-Schmidt procedure. Here I'm just showing how the procedure will look, but I will describe it further in the next slide. But basically, you start with a vector and you normalize it and save it. Then, to the other vectors of the basis, you start removing the contribution that is parallel to the first vector, like this. You're removing that part of the vector. And you iterate over all the vectors, and that will give you an orthogonal basis. And then what you do is you divide by the norm of the vector, and you get an orthonormal basis. The orthonormal vectors are denoted by this E. The starting vectors are denoted by this V. And the orthogonal vectors are denoted by these U vectors. You can see here that you're removing the parallel parts to the other vectors. Mathematically, this is equivalent to defining a projection vector, that, as you can see here, it is using this inner product and also the norm. And what you're doing is you start with the vector, you select one vector, and you save it. You say, this first vector will be part of my basis, so you just put it like it is. Then to the second vector, you need to take the original one and remove the part of this vector v2 that is parallel to this first vector u1. Then the third vector will be the starting vector minus the contributions of v3 that are parallel to u1 and u3, and so on. You can write this as a summation also, but the idea is that you're removing the part that is parallel to the other vectors. And how can you get the parallel part? Using the dot product and the projection operator that is defined here. Let's see an example of how this can be written in code. First, let's import the dot product or inner product. They are the same. And let's define this projection operator. The projection receives a vector u and a vector v, and it does the dot product between this v and u, then divides by the norm squared, or just the dot product between u and u. And just to clarify, this term here is just a number, okay? The dot product between two vectors gives you a number, and the division between two dot products gives you another number. But this part here is a vector. So you are basically scaling this vector u by this coefficient. Then the Gram-Schmidt procedure tells you that if you receive three vectors, v1, v2, v3, the first one, you just keep it as it is. Then you can normalize by dividing by the norm. Just to clarify, the norm of u1 is the same as the square root of the dot product between u1 and u1. Okay. Then for the second vector, you have v2, remove the projection, and then divide by the norm. And the same here. v3, you remove the projection of v3 with respect to u1 and u2, and then you divide by the norm. And how does this look? Sorry, let me go back here. Okay, so I have these three vectors, v1 that is 0.5, 0.2, 0, v2 that's 0, 0.8, 0.3, and v3 that's another vector in R3. These three vectors in the plot are shown in red. So you can see here they are not orthogonal. Yeah, this is a very tiny vector going like in this direction. This one is going in that direction. If you look them from this angle, you can see, well, you can see that those vectors are not orthogonal. They do not have right angles between them. Then you do the Gram-Schmidt procedure to these three vectors, and you obtain the orthogonal base, not only orthogonal, orthonormal base E1, E2, E3. That is the collection of vectors in blue, and those are orthonormal. You can see here you have a right angle. From this side you have another right angle here. If you look from the top, you have another right angle here. And the starting vector u1 is this one that is exactly the same as this, but scaled. So the only change between this v1 vector and this e1 vector is the scale. The first one, it had components 0.5, 0.2, but that's not a vector with a norm equals to 1. So that's why it's bigger. The blue one is bigger. Any doubts with this? Did you get what the Gram-Schmidt procedure is doing? Please, if you're not understanding, ask questions. Okay. So that's how you get a collection of orthonormal vectors from a regular basis. And well, here you can see the numbers, but of each vector. Can I put it in a more friendly way? Let's see. From NumPy import concatenate, and I think you can do this. concatenate. Okay, so to use concatenate, you need to do the first argument is a tuple of vectors, and then you need to the axis. So the vectors are b1 until b3. The axis is 1. Let me see. 0. No, it's not that. Maybe if I do this, the transpose, and then I do this. Let me go back when I define the vectors. I can make it work, but it's not that relevant. The only interesting part is that the vectors basically change to generate an orthonormal basis. I'll leave it as it is. Okay, so now I'm gonna talk a little bit about matrices and matrix manipulations. But first of all, we need to start with the basis. In what kind of application might I encounter such a process? There's an application that I'll see a few slides later that is called the QR decomposition, that uses the Gram-Schmidt process to get a factorization of matrices. I'll show it a little bit later. But in general, you want to get, or you want to do things with orthonormal bases, because let me explain a little bit more about basic matrix manipulations, and then I'll talk a little bit about the applications. Okay, so first of all, a matrix is just a vector that it has more columns. Okay, so it has m rows and n columns. This vector here, x, is just one column, and here it has n rows, like the example here. Maybe I can put it a little bit smaller so you can see. Okay, so you have this matrix with 5 rows, 3 columns, and you have this vector with 3 rows. To do the matrix vector product, the number of rows of this vector needs to be the same as the number of columns of the matrix. And the way you can do this product is basically row and column. You need to multiply this vector by this. For example, if you want to get the output, that it will have dimensions m and 1. By the way, you know why this output is m times 1 and not n times 1? Do you know how to infer the dimension of the matrix vector product? Well, a good way to, first of all, a good way to think why this resulting vector has m rows is that if you see the dimensions here, m times n and n times 1, this m and this n, they cancel out because you're doing a summation on the in this index. So you're basically having that dimension and adding it up just to 1. So this n and this n cancel out, and the resulting dimension is m and 1. So that's why you have m rows in B. So each coefficient B is a summation of these coefficients of the matrix, or equivalently, you can imagine as multiplying or doing the dot product between this row and this vector. So to get this number, the first one, you do the first row and the vector. For getting the second one, you do the second row and the vector. This one, the third row and the vector. Okay? So let's continue. How can you do this in Python? Let's define a matrix as an array. Here I'm the... Yes?
In the last slides,
Mm-hmm.
what happened with the last rows in E, in the first vector?
The last row, this one?
And what happened if you multiply with the vector, with the pink vector?
Okay, so each row, you need to do the inner product with this vector, right? So the first one, inner product this one, it gives you the first element of the result. The second one with this, the second one. And you do the same for each row, and the last one gives you the last component of this vector. Or you were doing, can you draw lines?
Yeah. Well, I know, but if the last rows of the pink vector are 0, multiplying by 0 is not 0.
Okay, so maybe let's do an example. If you have this matrix, this is my matrix A. The dimensions of the matrix are 2 times 2. Let's say I have this vector that is 1, 0. To get the, well, first, what's the dimension of the output? If this is 2 times 1, that means that these 2's will cancel out, and the result needs to be 2 times 1. Okay, so we'll have 2 rows and 1 column. Okay, so the first one will be the inner product between this vector and this vector. So that means this and this. You will get then 1 times 1 plus 2 times 0. The second row, well, it would be this one times this one. 3 times 1 and then plus 4 times 0. If you do the multiplications and everything there, you will get 1 and 3. Because if you multiply by 0, it will disappear. This goes to 0, this goes to 0. Maybe that answers your question.
Yep, clear. Thank you.
Okay, so if we now want to do it with Python instead of doing it by hand, for example, let's do the same example, 1, 2, 3, 4, and 1 and 0. You can define a matrix as a 2D array. So this is the first row, this is the second row, and you need to add these extra brackets to making it 2D. is like a list of lists. The same with x, 1 and 0. And if you do the dot product between a and x, that is the same as the matrix multiplication, you'll get this, 1 and 3. If you see here, I'm doing the matrix vector multiplication in two ways. One with the dot function, and another one using this. This add symbol is the same as the dot product in Python, but this only works for Python greater or equal to 3.5. And if we see the result we did by hand, we obtain the same, 1 and 3. Yeah, everything clear? Well, let's ask the opposite. Someone didn't understand this matrix vector multiplication? Does it work for any matrix multiplication? Yes. For example, well, in this example, we use a matrix that was with 2 rows and 2 columns. But if we did, for example, with 3 rows and 2 columns, 1, 2, 3, 4, 5, 6, we can use the same and it will work. The only case this will not work is if these dimensions here are not compatible. For example, if the vector that you're trying to do the matrix vector multiplication has not the same dimension as the number of columns of the matrix, it will not work. This, for example, if I try to do the matrix vector multiplication with this matrix and this vector, it would not work. If I add another row, and basically it will give you an error. This does not make sense. But if you always use vectors that has the same dimension as the number of columns, it will work for any matrix. Okay, this is a little bit like that. So what about matrix multiplications or products? You can think of matrix products as multiple matrix vector products. Let me clarify. Okay, here. Let's say you have the matrix 1, 2, 3, 4. And you want to do the matrix vector product with 1, 2. But you also want to do the matrix vector product with the same matrix, but another vector, 0, 1, whatever. The matrix product, if we were, for example, we had that this is the same as, in this case, it would be 5 and 7, no, 8 times 11. And here it would be 2, 4. But to calculate for vector 1 and vector 2, we did 2 operations, but we can do them at the same time by writing this as the same matrix A, 1, 2, 3, 4, and a matrix with first column B1 and second column B2. This now is a 2 by 2 matrix, and this now is a 2 by 2 matrix as well. And that will give me another matrix, 2 by 2, that the first column is the first result, that means 5, 11, and the second one is 2, 4. So basically the matrix-matrix product is a way of writing multiple matrix vector products. And the rules for that are basically we have the same 1, 2, 3, 4. This is our matrix A, and we wanted to multiply by 1, 2, and 0, 1. The first element of this new matrix, it would be the dot product between the first row and the first column. So in this case, it would be 5. For this element, we need to do this row and this column. So in this case, 2. For the second row, we need to use the second row and the first. So we will have 3 times 1 plus 8, 11. Let me put it here. 11. And for the last one, we'll have this one, that is the second row and the last column. And that is 4. Let's see if we can do this with Python now. Okay, so that's the rules. Here I showed basically a square matrix, but this also works with rectangular matrices. And as an example, let's use our matrix 1, 2, 3, 4, and the other one was 1, 0 to 1. 1, 0 to 1. And if we do the same, A times B, you get 5, 2, 11, 4. And as we can see, the elements were 5, 2, 11, and 4. So basically, this is the way you can do matrix-matrix products in Python. Clear? No? Can you explain something again? No? Yes? Perfect. So let's continue then. This is a little bit too large again. Maybe 65. Okay. So the QR decomposition. If you have a matrix A, as we have already seen, you probably can write a matrix as a product of 2 other matrices, right? And if these matrices satisfy some properties that we are interested in, that's called as a matrix factorization. So basically, you're writing this matrix A with these columns A1, A2, A3 as a matrix multiplication of this matrix Q and this matrix R, that in this case have 2 very particular properties. This matrix Q have orthogonal vectors, and this matrix R it's what it's called as an upper diagonal matrix. That means that it only has entries in this uppermost part of the matrix, forming a triangle. That's why it's denoted as an upper diagonal or upper triangular matrix. So we saw something to calculate from a collection of vectors A1, A2, A3, orthogonal vectors E1, E2, E3. Right? It was called the Gram-Schmidt procedure. So basically this QR decomposition is doing the same. Here I have an example of, let me go back so it will correctly be displayed. Can I do it so it's better aligned? I can put this up here. That's a little bit better. Okay, but the only important part is that we had vectors v1, v2, and v3. Those vectors are the same as the how we import matplotlib. Okay, so here I'm not showing how I imported matplotlib because I defined some other functions. Let me show how to do it. So to import matplotlib, you need to use the following line from matplotlib.pylab, import, and there you can import the functions you want, as figure, plot, and show. Okay, so basically I skipped this this cell because we have done it multiple times, but that's how you do it. Let's continue now with this. No, it wasn't, not this one, another one. Okay, so now with the QR decomposition. So, is there a way to import all matplotlib functions at once? Yes. To do it, you can do from matplotlib matplotlib.pylab import and then this. That is the same as all. Though it's not recommended to do this because matplotlib has like a million functions, and basically you could be defining a function that it has the same name as the one defined in matplotlib, and there could be a collision of names, and sometimes that can produce an error in code later. And there's another problem with importing all the functions in matplotlib or any package. That is that by loading all the functions, maybe there are like 11,000 functions that you will not use in your code. You will use just 1, 2, 3. So you are importing a very big package with all these functions, but you are just using 1 or 2. So it's better just to import the specific functions you will use to avoid name collisions and also overhead when you're loading the packages. So this line is not very recommended to import all the packages. Try to import only the packages you will use. So yes, so in this case, the relevant plots are defined by this function, but it will be basically plot, show, and maybe figure in this case. So remember how to do it, but try to import only the functions you will use. Okay. Jorge says that you need to, it's advisable to add what you are going to use to keep track of in your code. I'm not sure of what was that referring to, if was referring to something that I did in that time, or maybe you can talk and explain a little bit what you said. Okay. Perfect. Let's continue. So the vectors v1, v2, and v3 are the same vectors that we saw before, and we concatenate the vectors to get this matrix A the same way we saw here. The vectors are being concatenated as columns of a matrix. Those are concatenated as columns because the axis is equal to 1. You need to remember that in Python the index list starts from 0. That means that the rows are the index 0 and the columns are the index 1. Okay? That's why to concatenate vectors as columns you need to put axis equals to 1. Then, if we do the QR decomposition of this matrix A with the code QR, by default this QR function gives us the matrix Q and the matrix R. So to get just the matrix Q, I get the first element of the output. So let's see how the matrix Q compares to the vectors E1, E2, E3 that we had in our Gram-Schmidt procedure. You will see here, they are very similar. Let me put this in another slide. It's a little bit too crowded. Another one. Okay, so the vectors in blue are the results of our Gram-Schmidt procedure, and the vectors in red are the results of the Q matrix, of the QR decomposition. And as you can see, they are basically the same. The only thing that could be different is the direction of the vectors. For example, here these are pointing to the other direction, basically. If I multiply the first two by -1, they are exactly the same. Here. As you can see, those are exactly the same. The only thing that could change is that it was pointing to the other way, but it's basically the same vector. So that's an application of the Gram-Schmidt process. You can do matrix factorization, and the factorization has a very interesting property that one of the matrices is orthogonal. Not only the vectors here are orthogonal, but the whole matrix is called unitary or orthogonal, because the matrix product between this matrix Q and itself but transposed give us the identity matrix. We can look at this maybe here. If we do Q dot Q transpose, we can see here that we have 1s in the diagonal, and these very, very tiny numbers are basically 0. Okay, if you have something that is lower to 10 to the minus 15, it's basically 0 to a computer. So, for example, from NumPy import concatenate, we can also import round, and we can round the result with, I don't know, digits 5. I'm not sure how to use it. 5? Yeah. And basically you see that the matrix Q times itself but transposed is a diagonal matrix. And this is with even 10 digits. In 20 digits it starts like this, but basically with a precision of 15 digits is equal to the identity matrix. And the same goes for the opposite. The transpose here, and you put it in the other matrix. Okay. So that's the QR decomposition. Another way of interpreting this matrix vector product is to think of it as a linear combination of the columns. You have a vector X and a matrix A composed by these columns A1, A2 until A3. The matrix vector product will be the same as the coefficients of X multiplied by the columns of A. So let's have an example here. In our previous matrix multiplication, we saw that the result was 1, 3. An equivalent way of think of this is to think this matrix vector product as the first element of the vector, here is 1, times the first column, 1, 3, plus 0 times the second element of this vector, the second column. And this will be exactly the same as doing this. So it will give us the same result. The benefit of the matrix vector product in this way is that we are basically transforming the input by a linear transformation. We have a vector here X, and we are doing a transformation to obtain another vector. Let me see if I have an image for that. I think I have here. Let me go back. Okay. So these red arrows are the columns of a matrix A. The green arrow is the result of the matrix vector product. And the blue arrow is the input, or the vector X. And by applying this matrix A to the vector in blue here, X, we're doing a transformation to another vector in green. Axis equals to, in which part? Here? Concatenate axis equals to 1. That was the question? Yes, okay. Yeah, it's the same. We're basically using vectors and concatenate them as columns to get a matrix. Okay. To see a little bit more about linear transformations, please look at this video. It will explain it better than I could possibly do it, and it has very cool animations. So if you want to learn more about how to interpret a matrix as a linear transformation, please look at this. I will not put the whole video, but maybe it has a cool animation that I could quickly show you.
Column BD is the place where the second basis vector lands. When we apply this transformation to some vector xy, what do you get?
Can you listen to the audio, or I need to share it? Okay, now.
As the place where the first basis vector lands. And that second...
So you have two vectors. In red, the vector VD, and in green, the vector AC. Those are columns of a matrix.
Column BD is the place where the second basis vector lands. When we apply this transformation to some vector xy, what do you get? Well, it'll be x times AC plus y times BD. Putting this together, you get a vector ax plus by, cx plus dy. You could even define this as matrix vector multiplication when you put the matrix on the left of the vector like it's a function. Then, you could make high schoolers memorize this without showing them the crucial part that makes it feel intuitive. But isn't it more fun to think about these columns as the transformed versions of your basis vectors, and to think about the result as the appropriate linear combination of those vectors? Let's practice describing a few linear transformations with matrices. For example, if we rotate all of space 90 degrees counterclockwise, then I hat lands on the coordinates 0, 1. And j hat lands on the coordinates -1, 0. So the matrix we end up with has columns 0, 1, -1, 0. To figure out what happens to any vector after a 90-degree rotation, you could just multiply its coordinates by this matrix.
Did you get that? Or were you listening, or the audio was not being shared?
Yes.
Yes? Okay. And did you understand what he said?
For me, yes.
Yes? So basically, a matrix can be described as a linear combination or a linear transformation of the canonical vectors that here he's calling them I hat and j hat, but you can think of them as 1, 0 and 0, 1. And if you apply the linear transformation to those vectors, for example, in this case, he's showing a 90-degree counterclockwise rotation, you'll have the columns of the matrix. So in this case, a 90-degree counterclockwise rotation is described by the matrix 0, 1 and -1, 0, because those columns are the place in which the canonical vectors will land after the transformation.
Here's a fun transformation with a special name, called a shear. In it, I hat remains fixed, so the first column of the matrix is 1, 0. But j hat moves over to the coordinates 1, 1, which become the second column of the matrix. And at the risk of being redundant here, figuring out how a shear transforms a given vector comes down to multiplying this matrix by that vector. Let's say we want to go the other way around, starting with a matrix.
Okay, so I'll leave it right there. If you're interested in learning more, go to the 3 Blue 1 Brown YouTube channel and look at all the videos that he has about linear algebra. Okay, so why are matrices so important? We saw one example that a matrix can model a linear transformation. So what things can be modeled as linear transformations? Basically any system that is discrete and linear. A matrix is a way to model linear systems. Can you think of a linear system? You have an example of a linear system? One could be a 90-degree rotation or a shear transformation. For example, I'll ask you this. If you have a photo and you want to give the photo perspective, like the part at the top goes smaller and the part at the bottom goes larger, and you will see it like that. Do you think that's a linear transformation or not? Applying perspective to something, do you think is a linear transformation? Not sure. Okay, so let's see. Perspective transformation. This will be a little bit counterintuitive, but if you see, for example, this. You have a source image, you do a transformation, and you get this. At first you could think that this is a linear transformation, but in fact it is not. The reason why is because you need an additional component. If you have a 2D space, vectors in 2D, to do perspective, you need a 3D matrix. So basically you need to transform the domain to do this 3D perspective. So counterintuitively, the perspective transformation is not linear. Another example of a transformation that is linear is, for example, or a system that is linear is the magic square. Have you heard of a magic square before, or this is the first time you heard about magic squares? Never before? Well, a magic square is a puzzle that basically you have a grid. Here I'm showing a 3x3 grid, and your goal is that each row needs to add to the same, each column needs to add to the same, and the diagonal terms needs to add also to the same. It's like a Sudoku. It's a precursor of the Sudoku. And the solution for this is the one I show here. And you can do a magic square of any size. And why this is a linear system? Because each of these numbers can be associated with an equation that is the number plus this one number and this number is equal to something. So you're basically multiplying each number by 1 and then adding them together. That would be equivalent to adding or multiplying by a matrix, only with ones in specific positions. Okay, so that's not very exciting. A more exciting example is the computerized tomography. In the computerized tomography, let me see if how the video is working. Okay. It's not stopping. Let me leave it that instant. If you have, for example, a body, here's a head with brains and eyes and everything. These red lines are X-rays. The X-rays have a path that goes through the body, and basically what it's doing is adding all the elements inside until it goes here. Let me I will not explain the physics, but basically the X-ray, what it does is that it integrates over a line. Integration is the same as summation. So at the end, you have the summation of all the properties of the tissues over that line. And you have that over all the lines. Like this. You have a shadow of the body. Then, why it's not working? This? Maybe? No. Okay, here. And the computerized tomography, in contrast to just regular X-rays, it's like you have an X-ray in every angle. So you're rotating your X-ray source and getting the data at the other side. And basically what you're acquiring is the thing you see here. This is called a sinogram. So in each column, you have the projection of the 2D image, or the addition or summation of all the pixels that goes in each of these red lines. For example, if the number of rays is equal to here 20, this result would have 20 pixels by the number of angles you are acquiring. And obviously, if you have a summation, this would be a linear system, and linear systems can be represented as a matrix. So basically, you can solve a matrix vector system and get from the sinogram, or the data that you're acquiring, how the body looked from the inside. You're measuring from the outside and inferring with linear algebra what was happening in the inside. Another example of linear systems are, well, basically all the types of medical imaging, like magnetic resonance imaging, ultrasound. You can also think of it as a linear system, and so on. Okay, so we have 5 minutes. The activity was to solve a Sudoku. So you have this, and you had to program a way to solve this 2x2 Sudoku by knowing that each of these square grids needs to add to 10. In regular Sudoku, you need a bigger number here, but here as 1 plus 2 plus 3 plus 4 equals to 10, each of these are the same as 10. In the Sudoku, you also have that the rows needs to be add to 10, the columns needs to add to 10, and so on. So maybe you want to try to program this with matrices and solve the linear system. You can do it as a mini homework, but I'm sure you have enough with the regular homework. So maybe let's show the solution of this activity in the next TA. And here you can try to do a more advanced problem in which you need to solve the magic square of size n. So you need to create a function that you have as input n, and it will give you the magic square of size n. And if you're interested in magic squares, you can learn more by looking at the Wikipedia page. Okay. Let's leave the recorded part until here. So, goodbye.